All right. Our next speaker is Sahil Hegde from UCLA, who will talk about establishing a census of star formation across cosmic time with Roman. Thank you.
Where's a few? Where's a few? Oh, over here. Okay. Okay. Perfect. Yeah. Thank you so much. Oh, I see we've switched pointers. Hello? Okay. Okay. Thanks. All right. So, as I said, my name is Sahil. I'm a rising sixth-year PhD student at UCLA. Everyone okay? All right. Okay, yeah, I'm a rising sixth-year PhD student, hopefully not too shocking, at UCLA, working with Steve Furlanetto. And I've spent a lot of my PhD thinking about star formation at very high redshifts, so thinking a lot about POP3 stars. And now I've been thinking a little bit more about galaxies across time, and I'm really excited to be able to share some of that work and taste of how Roman can maybe shed light into star formation from the beginning of the universe all the way to today. So, cool. Okay, so I promised a census of star formation across time, so I have to show a timeline of the universe, or at least my reductive theorist view of it. So here I'm showing the high redshift universe at the far left, and then the local universe at the right. And so the way I think about star formation is starting with primordial pristine gas from which the first stars form. And because of this primordial hydrogen helium dominated gas, we think that the first stars formed to be very big, blue, and lived very short lives. They lived these short lives, exploded as POP3 supernovae, and started the process of global chemical enrichment across the universe. And through successive generations of star formation, from low metallicity out to more chemically mature populations, we get these stellar populations, POP1 and 2, that we've seen sort of dominating the local galaxy population, and with our even high redshift observations today. So in my talk, I'm going to focus on two different parts. First, I'm going to talk about POP3 stars and explore how, as I said, we have a lot of things that we think about POP3 stars, and this is basically an exclusively theoretical field to this point because we really don't have any convincing observational constraints on the demographics or properties of the first stars. Even with JWST bringing us closer to this era, we still haven't really placed direct constraints, so there's a lot of work to be done, and I think Roman can still shed some light on POP3 stars, even though it may not reach the super high redshifts where these stars are really going to be dominating the star formation budget of the universe. Then I'm going to move on and for the second phase of the talk, focus on star formation throughout the rest of the universe's history, where we have comparatively a large amount of data, but I'm going to describe how there may be some systematic uncertainties that still persist in our observations and highlight how we might be able to use some independent analyses with Roman observations to pin down some of those uncertainties. And since I have to cover 13 billion years of history in now 9.5 minutes, I'm just going to click right through it. Okay, so for the first part, high redshift star formation. So a lot of my PhD has been driven by this question of trying to understand how we could build an efficient model for early galaxies that also self-consistently includes the first stars. And I've highlighted the word efficient here because of that point that I was saying at the start, which is that we really don't know that much about POP3 stars. A lot of our models predict very different things. We don't know things about the POP3 IMF, the star formation efficiency, feedback, and the list goes on. And so because of that, I was really focusing on building a model that's efficient enough that we can sort of flexibly explore these uncertain parameters and understand when and where POP3 stars will form and use that to optimize our observations to be able to start to build some constraints from a wealth of observations across the electromagnetic spectrum. So to reduce 5 years of PhD work into one slide, this resulted in, not nothing, but this. It resulted in this model, which I've called the ABCD model, or an analytic bathtub for cosmic dawn. And so this model is meant to be a simple, interpretable, and flexible framework to model star formation from the first dark matter mini halos of 10 to the 6 to 10 to the 7 solar masses at very high redshift, and evolve their star formation histories down to the end of reionization, and be able to efficiently then vary parameters and see how the resulting star formation histories are sensitive to our choices for star formation enrichment, feedback, and so on. So one sort of example of an output that we can get from this model is the, whenever that sharpens, the global star formation rate density. So here I'm showing the star formation rate density on the vertical axis as a function of redshift, starting at, I think, higher redshift than most people have talked about so far, so from redshift 40 down to redshift 5. And I'm showing the POP3 star formation rate density in red and the POP2 in blue. And I further subdivided the POP3 SFRD into the contribution from small molecular cooling halos as a dashed line and comparatively larger atomic cooling halos in a dotted line. And so what we can see from this is that our model predicts that, as we expect, star formation or POP3 star formation dominates the budget of the universe at very high redshifts. This is taken over by POP2 at around redshift 15 to 20, where we're now starting to get a lot of JWST observations of high redshift galaxies. But even despite this, we still have this plateau or kind of ongoing POP3 star formation out to the end of reionization, suggesting that if we can get observations of galaxies in this era, and if we look for the galaxies hosted in more massive halos, we might still be able to see POP3 stars even out to these later times than folks have maybe previously thought about. So, given the focus of a lot of our talks this morning, it may come as no surprise. I like how you get a little bit of suspense every time the slide changes. Given what we talked about this morning, that we can maybe think about POP3 stars and constraining the POP3 stars using transients. So here I'm showing how we can combine our star formation rate density predictions with some choices for a flexibly assumed POP3 IMF. And if we combine that with a light curve for POP3 supernovae, and specifically here I'm showing some sample parent stability supernovae light curves, then we can make forecasts for what Roman could be able to see. So one such prediction is shown here, where I'm comparing now the cumulative parent stability supernova rate from POP3 stars from redshift 16 down to redshift 5. And in purple and red, I'm showing two different JWST surveys, which, because of their smaller field of view but deeper sensitivity, will be able to get to higher redshifts, but won't really measure a statistical or, we'd be very lucky to see POP3 supernovae. If we then instead look for wider field surveys like Euclid or Roman, we, as was mentioned earlier today, we may be able to see tens or maybe if we're lucky, hundreds of POP3 supernovae in this sort of reionization era. And if and when we're able to measure these, then we can start to use them to pin down the POP3 star formation efficiency, IMF, and so on. Cool. So that's a little taste of how Roman might be able to shed light on the high redshift universe and how we can use our simple galaxy models to constrain physics that way. And so now I'm going to move on to the second part, thinking about star formation throughout the rest of the universe's history. And here I'm going to focus on a fundamental galaxy relation, the star-forming main sequence. And so to set the stage, I want to summarize a problem that I recently came across in the literature, which is that this fundamental galaxy relation, the star-forming main sequence of the relationship between a galaxy's star formation rate and stellar mass, despite its fundamental importance in galaxy evolution, is actually fairly kind of uncertain. And so if we look at a compilation of observational measurements, here I'm showing JWST observations with spectroscopy, photometry, pre-JWST compilations, and other analyses, we see distinct evolutions in over redshift. We see different normalizations and different shapes to the main sequence. Going along with this, there's also been a longstanding sort of underprediction of star formation rates at fixed stellar mass from theoretical models. So, I should say, this is the specific star formation rate of 10 to the 9.5 solar mass galaxies from redshift 9 to redshift 0. And here now, these red curves are showing a variety of different theoretical predictions, and they all basically systematically underpredict the observed relations, even with all of the uncertainties in the observational inferences here. Another way to see this issue is if we think about the star-forming main sequence in the context of other galaxy fundamental relations, like the stellar mass function, which I'm now showing here on the right. So here I'm showing the stellar mass function at redshift 3 as a dashed line, and at redshift 1 as the solid line. And I could do this sort of exercise where I take the star-forming main sequence, or one of these observed ones, and I ask whether it's self-consistent with the stellar mass function, since the evolution of the stellar mass function encodes the buildup of star formation over time from the main sequence. So if I do that, and I take one of these literature compilations that I showed, I get something like this dashed line, where I see that this predicted star-forming main sequences actually produce way too much stellar mass. And if I use a different model, a different one of these observed main sequences, it does a little bit better, but it still doesn't work perfectly. So this motivated me to ask a different question, which was, if I wanted these two relations to be self-consistent, what does the star-forming main sequence need to look like in order for the stellar mass function to be consistently evolving over time with it? So to make a long story short, I took a compilation, I compiled a bunch of stellar mass function measurements from the literature using JWST and pre-JWST data, compiled a redshift evolving stellar mass function from redshift 0 to redshift 9, and then effectively took the time derivative of these measurements and got this prediction for the specific star formation rates over time, where in black, I'm showing that evolution. And so one thing that you can maybe immediately see from this is that this sort of straddles the divide between the theoretical and observational predictions that I was showing. And one interesting thing is that if we compare my black line from the stellar mass function to these points, which are JWST-based spectroscopic inferences of the main sequence, we're starting to actually see some convergence between different measurements and some self-consistency in these relations. So now with JWST, we're maybe starting to get a more cohesive or self-consistent picture of these fundamental galaxy relations. But these mass functions, as you may be able to guess, or this sort of method is still susceptible to cosmic variance, or the field-to-field variance in galaxy counts because of clustering. So Steve Finkelstein gave an excellent overview of this on Monday, and so I don't really need to go over it too much, but here I'm showing an estimate of those same stellar mass functions, but now with the uncertainties due to cosmic variance colored on top of them. So you can imagine that then if I take what are small field of view JWST surveys and I switch to what we might be able to measure with Roman, we won't go quite as deep, but we will be able to tighten the uncertainties due to cosmic variance, and this can make this method, which gives us a sort of independent check on our star formation rates and star formation history of the universe, we can make that sort of inference a little more robust and can continue to do this test phenomenologically of whether our star forming main sequences are consistent with other galaxy relations that we've measured. So from this, we can see that Roman can, with observations of high redshift transients, be able to pin down star formation at really high redshift, and could also help us shed light on the evolution of galaxies from the high redshift universe down to redshift 0. And I'm really excited to see what we're able to learn with that. So I'm going to, leave my conclusions up there. And those are two of the papers which summarize a lot of the stuff that I've talked about. So thank you.
All right, thank you very much for the great talk. We can take one question while maybe Kalina sets up for the next talk. Okay, Wangi.
Thanks. This is just a question for some quick sanity check. When you are showing the star formation rate, observe the star formation rate, what kind of a star formation rate observation you're actually talking about? Is it like a comparison in between like a C plus to the other those kind of things. So the observation itself for the star formation rate can be actually wrong. I mean, there are a lot of the uncertainties over there. So I just wonder what is the uncertainties and if it is actually agreeing with your theory.
Yeah, so you're exactly right that there are a lot of uncertainties in what sort of calibration you choose to infer the star formation rates, whether you're observing galaxies in the UV, IR, or what have you. And that's some of what leads to these systematic uncertainties. If you use some kind of SED fitting or something, you get some different answers as well. And there's also uncertainties to stellar mass inference based on what kind of filter coverage you have. So these two lines, which are compilations of other star formation rate measurements from the literature, have tried to do that sort of characterization of uncertainties. So the compilation that they're doing is bringing everything into a consistent basis of different calibrations. But what that doesn't ensure is that the basis that you've brought the measurements into is necessarily the true underlying star formation rate of all of the galaxies in your population. So you could still be systematically biased in some direction. And stellar masses tend to be at least a little bit less sensitive to some of these biases. And so we can use the mass function as a semi-independent check of whether or how sensitive to the biases our star formation rates are. But yeah, that's a great question. This is like very highly sensitive to that. So I think these sorts of tests are really useful to at least see if we can get the same answer from different angles.
Great, thanks so much. All right, let's thank Sahil again.